Let's see what happens when we have less than 8 electrons in the outer shell, which is quite rare, of course, because most atoms won't have a full octet. And we've done that, so you can have 4 bond pairs, or you can have 3 bond pairs and a lone pair, or 2 lone pairs, 2 lone pairs. But let's think about beryllium chloride, okay? Beryllium chloride. Beryllium's in group 2 of the periodic table, but this isn't ionic, it's covalent. And the reason for that is because the Be2 plus ion got a double charge on it, and it's absolutely tiny, and it's got a very high charge density, so sometimes beryllium forms covalent compounds. Right, so we draw a dot cross diagram for that. It will look a bit strange, but it's very easy. So a dot cross and a dot cross. Now beryllium has only got 2 electrons, is in group 2, so we've drawn both beryllium's electrons, both 2 dots there, or 2 crosses. And the chlorines, well, they've got 7, so I need to draw 6 more for each chlorine. Now that beryllium looks quite strange there because there's only 4 electrons in their outer shell, the outer shell, which of course usually wants 8. So you can probably guess what the shape of that molecule is going to look like. Both those, so you've got 2 bonding pairs, haven't we, there? And those electrons want to get as far away from each other. There's pairs of electrons want to get as far away from each other as possible, because they're both negatively charged. So you get one bonding orbital like that, and another one like that. The bond angle between those is, well, it's a straight line, so it's going to be 180 degrees. And the shape of that molecule is called linear. So that is rare, but quite straightforward and easy to understand. Let's see what happens now when you've got 3 bonding pairs. And a good example of that is aluminium chloride. Now, aluminium it's covalent, okay? And the reason for that is, right, because Al3 plus ion is very highly charged and pretty small. Okay, so sometimes it forms covalent compounds, even though it's a metal. So we drew a dot cross diagram for that, aluminium. Right, where they overlap, a dot and a cross, a dot and a cross, a dot and a cross. Each chlorine has got 6 more, hasn't it? So I'll draw them for that one. I won't draw it for all of them. So that's aluminium chloride. Again, it looks quite strange because you've only got 6 electrons in the outer shell. So it's got 3 bonding pairs. And how are they going to get as far away from each other as possible? Well, they'll all fit onto a flat piece of paper. You're going to have, so if you have one there, one bonding pair there, another one there, and another one there. Right, now the bond angle is going to be 120 degrees because if you think about it, you've got a full circle there, haven't you? Divide it by 3, 360 divided by 3, 120, pretty straightforward. And that is called trigonal planar. And just to point out, like a very common mistake people make, they get asked, what is the shape of ammonia? And they don't draw a dot cross diagram. They think, all right, oh, it's 3 bonding pairs, you know, so it's trigonal planar, but it's not, because they've forgotten their nitrogen has got a lone pair. So it's 4 pairs of electrons. So it's going to be, like we said on the previous video. So it's like that. It is not trigonal planar. Now let's think about when we've got three pairs, but one of them's a lone pair, and I have to think it's a fairly exotic species for that. So we have CH2, which doesn't exist except as a reactive intermediate. You know, it's not stable. You can't have a bottle of CH2. It fleetingly exists, but it does exist. So we draw a dot cross diagram for that. We've got carbon there, 2 hydrogens, a dot and a cross where they overlap. Now carbon is in group 4, so it's got 4 electrons. I've only drawn 2, so it must have another 2 electrons. It's got a lone pair there. So you've got 3 pairs there. You've got 2 bonding and 1 lone pair. So the lone pair causes more repulsion, doesn't it? Because it's bulbous shape. So we use this as our sort of guide to what it's gonna be. Right, we're gonna have the carbon there. Here's our bonding pairs, and we've got our lone pair, which is pushing down. Not pushing down, pushing these 2 together, making the bond angle a bit smaller. So it's going to be probably something like 118. And you would describe that as being V-shaped. It's a different V-shape. It's a different V-shape to the water molecule, which we came across before, because of course that had 2. We'll just write it down there, H2O. That wasn't 2 bonding pairs and 1 lone pair. That was 2 bonding pairs and 2 lone pairs, and the bond angle there was 104.5. So, yeah. Okay, so that's all we have to do about things with less than 8 electrons. So we just do a little summary of what we've done so far. If we go to this one. Right, so what we've just done there, number of pairs 2, we've got beryllium chloride, yeah, linear 180 bond angle. Then we go to the three pairs, aluminium chloride, trigonal planar 120, symmetrical. Then if we have a lone pair in there, like here, we end up with the bond angle being a bit smaller. Let's go to those ones with 4 in them. Okay, so the previous video, 4 bond pairs, methane tetrahedral, 109.5 bond angle. Ammonia now, if you end up having a lone pair in the molecule, what does it do? It pushes the bond angle down to 107.5. Water, you've now got 2 bond pairs, two lone pairs, it pushes down even further, and it makes it about 104.5. And you can see here, there's one, you've got 5, but I'm going to do that in the next video because it's going to make this one a bit too long. Okay, so we'll leave that there.